Now, the third example we're going to do is a door code detector. So this is the same as exercise 2 from the week 14 practice exercises. So we're going to design an FSM, a finite state machine, that has one input, it's a 4-bit input, the input N, and has one output, the output open. The input N indicates a number entered on a keypad, and the open output should assert to open a garage door. So the FSM should assert the open output whenever this given sequence is detected. So 5, 9, 2. So 5 followed by 9 followed by 2. And you can assume a new input is received just after each clock edge. So the first thing we do is draw a black box diagram. So we have our FSM, black box. Always start by putting the clock input and the reset input. It's not going to work without those two inputs. And then we have our 4-bit input N. We can write that as N 3:0. And then we put a /4 to indicate that those are 4 wires. And our single output, a 1-bit output, open. So now we need to draw the state transition diagram. So the state transition diagram is going to have, well, you start with a reset state. We call it SR. That's the state we're in when we haven't detected any part of the sequence. And we, again, start by drawing what we're looking for. So we'd like to detect N equal to 5, followed by, so we'll call it the S5 state. If you're in the S5 state, you know you've detected the 5 already, followed by N equal to 9. Remember, our sequence is 5, 9, 2. So if we get a 9 after we've seen a 5, we can be in the S5-9 state to indicate that we've seen both the 5 and the 9. Now we're just waiting for the last input, N equals 2, and then we can go to the S5, 9, 2 state, and in this state, we want to assert open. Okay, so we always start by drawing our FSM for what we're trying to detect. So in this case, we're trying to detect 5 followed by 9 followed by 2. So 5 followed by 9 followed by 2. And now we can write all the exceptional cases. So what happens when we don't get that sequence? So remember, if we just leave it like as is, well, now what happens if we're in the SR state and we get something other than 5? So N is not equal to 5, it's something else. Where should we go? Well, at that point we haven't detected any part of our sequence, so we'll go back to the reset state. If we're in the S5 state, we've already received our 5, we're looking for a 9, but if we don't get it, we can also go back to the reset state. N is not equal to 9. If we're in the S5-9 state and we don't get a 2, we can also go back to the reset state. And once we've detected our sequence, we can just go back to the reset state and look for the next 592 input. So here that is written out nicely. And now we're going to draw the state transition table. Basically take our state transition diagram and turn it into a table. And so again, as always, we have our current state on the left with our inputs, and our next state on the right. If our current state is SR and our input is 5, so our N input is 5, then the next state should be S5. If we're in the SR state and we don't get a 5 on our input, then we want to go back to the SR state. Now we look at S5. If we're in the S5 state and we get a 9, then we go to the S5-9 state. If we're in the S5 state and we don't get a 9, well, we go back to the reset state, SR. If we're in the S5-9 state and we get a 2 here, then we go to the S5-9-2 state. If we're in the S5-9 state and we don't get a 2, this transition, I'm going to go back to the SR state. if we're in the S592 state and, well, it doesn't matter what happens on the input, we're going to go back to the reset state. So we've made some assumptions about this FSM. For example, we could make it more complex and say, well, if we're in the S59 state and we get a 5, maybe it goes to here instead. And this is the case where it's not equal to 2 and it's not equal to 5, then it goes back to the reset state. But we start with a simple option. So for example, on your smartphone, if you have a code, you enter 595. It doesn't put you back at that first, allow you to start the sequence. You actually you've already messed up. 59, well, at that point, 59, you're in this state. If you enter 5 at that point, now it goes to the reset state. It says, yeah, this code is not correct. Okay, so let's talk a little bit about what this means for the input to be 5. Well, how do we detect that this is a 4-bit input, so N3 to 0? How would we detect that it's 5? Well, if it's 5, it's this value. How do we detect that? Well, N3 would be low, N2 is high, N1 would be low, and N0 is high. So we could do that. Make a gate that outputs a 1 if N3 is low, N2 is high, N1 is low, and N0 is high. In fact, it would look like that. Basically, like this, N3 low, N3 bar, N2, N1 bar, and N0. That would be the is 5 output, for example. Well, then how do we do this thing where it's not 5? How do we detect that it's not 5? Well, here we go. Inverter is not 5. So now we can choose some state encoding. For example, the state encoding. Well, we have 4 states again, so we need 2 bits of state. If we had 5 states, we would have needed another bit. If up to 8 states would need 3 bits. Up to 16 states would need 4 bits, etc. So if we had, for example, 13 states, well, certainly can't do it with 3 bits because that would only allow me to encode 8 states. So we'd need 4 bits for 13 states. We wouldn't use all the encodings. Okay, so for 4 states we need 2 bits, and we choose this encoding. SR is 00, S5 is 01, S59 is 10, and S592 is 11. And then we encode our unencoded state transition table just by replacing those state bits. And I'm writing out my N3:0 in binary now. Okay, so just as before, we have that one-to-one correlation between the unencoded and encoded state transition table. And now we can write our equations. So S1 prime is going to be 1, S1 bar, and S0. And, well, we want to detect that 9 here. So N3 and N2 bar and N1 bar and N0. Or this next one, S1 prime, S1 and S0 bar, and N3 bar, N2 bar, N1, and N0 bar. Our next state bit, S0 prime, is going to be, well, here's a 1, S1 bar and S0 bar, and N3 bar and N2 and N1 bar and N0. Or, well, that same case for that one here. S1 and S0 bar, N3 bar, N2 bar, N1, and N0 bar. So we have this duplicated term, and we can use that to our advantage in that we only have to create that output once, and then we can use it twice, once for each equation, for each circuit. here that is written out nicely. Again, here's the common term. These last two terms are common for both equations. And now we can draw the output table. So we're going to have the current state on the left and the output on the right. In this case, we have a single output. You could certainly have more than one. In this case, we just have one, the open output. Current state, I'm just going to go directly to the encoded, but you can write that SR, S5 was 0, 1, S59 was 1, 0, and S592 was 1, 1. And our output should be asserted only in the S592 state. Zeros in the other ones. So again, we get open equals S1. Remember these are the current state bits, S of 1 and S0. So S1 and S0. So both of those state bits have to be high in order for the open output to assert. So here we have the unencoded output table and the encoded output table, and then a reminder of what the encodings are. And our output equation. So now we're going to take our equations, our next state equations, and our output equation. Could be more than one output. In this case, we only have one. And turn this into a circuit. So we're going to have always start with our state register. Again, always put in the clock and reset. In this case, we have two state bits, S1 and S0. I'll pull those around to use in our next state logic. And we're also going to pull in our inputs, our 4-bit input. And 3, and 2, and 1, and N0. And again, we can also label these state bits S1 and S0 so we don't forget. But again, those are not inputs, those are pulled around from the right side of our state register. So now we're going to create our next state bits, so S1 prime and S0 prime. Well, this first term is a 6-bit and shaped gate. So we'll do our 6-bit and shaped gate. We have another 6-bit and shaped gate. And then we have a third one. So 1, 2, remember these two here are the same. So I only need to generate that term once. And then the third term that we're going to create there. So the first one has not, true, true, not, true. This one has a true, not, true, and not. So now we're going to grab our terms, and these will be ORed together for S1 prime. So we're going to get S1 bar and S0 and N3 and N2 bar and N1 bar and N0. That's this term here, the first term. Now we're going to get the next term, and we get S1 and S0 bar and N3 bar and N2 bar and N1 and N0 bar. Now we're going to OR that term with the last term. And so this one we're going to have a bar, 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 true, bar, true. So S1 bar and S0 bar and N3 bar and N2 and N1 bar and N0. Okay, so we're done with our next state logic here. Determined our next state bits. And now we need to get the output. So our last one here, we use just the current state. This is the current state. We also called this just the state. According to our equation, open should be equal to S1 and S0.